Hello, everyone, and welcome to our virtual summit, Accelerating Gas Detection in Health, Safety and Environment. Thank you very much for joining us this morning or afternoon, depending on where you're tuning in from. My name is Anna, and I'm the editor of Health and Safety International, Health and Safety Middle East, and AWE International magazines, which are our portfolio of international health, safety and environment publications. And I'm delighted to be hosting this exciting summit for you today. As we all know, gas detection and measurement technologies play a vital part in both the safety of workers and our understanding and monitoring of ours and other impacts on the environment. HSE relies heavily on accurate and reliable measurement to keep people safe and provide important data to decision makers. In this webinar, we not only aim to help you excel your current HSE strategies, but also unlock the latest research and development in gas measurement and detection. Our speakers will cover aspects across personal gas detection, atmospheric monitoring, and new technologies and innovations. So I'm confident that everyone will be able to take something away from today's summit. Just before I move on to our first speaker, I'd like to say a special thanks to our sponsors for this webinar, who are International Gas Detectors, WatchGas, Recon Kiki, and AlphaSense, who are all market-leading manufacturers of cross-industry gas detection solutions. So do please check out their services and product offerings at the end of the summit. Also, if you have any questions for our speakers throughout the webinar, then do please pop them in the Q&A section, which can be found at the bottom of your screen, and we will try our best to get as many answered for you as we can at the end. If you have a question you'd like answered directly, then do please feel free to message our panelists in the panelists chat window with your question in email so that they may reply to you after the webinar has ended. So, without further ado, please allow me to hand over to Dr. Oksana Tarasova, Chief Scientific Officer at the World Meteorological Organization.
Okay, thank you very much for the invitation for this webinar. It's an honor and pleasure for me to speak to you. And I will be talking about the atmospheric composition observations for decision making. So looking at the atmospheric composition from the broader environmental perspective. So why do we need to look at the atmospheric composition? And this is the thing which often people call the atmospheric pollution or some other related issues. Well, the point is that atmospheric chemical composition is an intimate part of our life. So we are actually breathing the air around us, and what we breathe is absolutely important for our health. But that spans the problems from, let's say, very local problems when we talk about the plume dispersion or urban smoke, where the changes in atmospheric composition happen on smaller scale. But if you look at the more regional issues, for example, change in visibility, or for example, the forest fires, which we observe now happening in Canada and have implication for the regional air quality, or the deposition of the atmospheric constituents to the soil that actually impact the biodiversity and soil productivity. But it goes only larger, it goes to the whole planetary scale. For example, the changes in atmospheric composition, for example, emissions of the ozone depleting substances, they lead to the destruction of ozone layer across the globe. We have the major greenhouse gases, methane, CO2, and nitrous oxide, and many other gases, which change the climate globally. And we also have some other pollutants which change the biogeochemical cycles on a global scale. So it is the interface where the humanity actually interacts with the environment, which is happening through this connection on the atmospheric composition, but also it is an impact which we see also happens in this area. So basically, the changes in atmospheric composition and the changes in the load of different constituents in the atmosphere gave a rise to the several environmental regulation and several environmental conventions. For example, the observations of the ozone depleting substances are regulated as a part of the Montreal Protocol and Vienna Convention. When we look at the concentration of the traditional pollutants like tropospheric ozone or nitrogen oxides in the atmosphere, they give a rise to the convention which regulates the pollution, and that's the core of the Convention on Long-Range Transboundary Air Pollution. And even if we look at the Paris Agreement, and if we look at the United Nations Framework Convention on Climate Change, that convention was driven by the observational data coming from Mauna Loa and saying, hey, look, the concentration of CO2 in the atmosphere has been rising and it will drive substantial changes on the climate system. So the observations of atmospheric composition is the core of those environmental conventions. But let's take a look at the Paris Agreement as one of the examples where the observational data is the core. So the Paris Agreement talks about the overarching ambition to limit the global average temperature increase by 2 degrees and strive to limit it even to 1.5 degree. Yeah, everybody heard the news that because of these emerging El Nino, there were a couple of dips when the global temperature already was touching 1.5 degree. So the control under the Paris Agreement is done by the control of emissions, and the balance should be reached between anthropogenic emissions by sources and removals by sink of the greenhouse gases by the mid of the century. And then the commitments are done through the national determined contribution, which is what is a country are ready to do to achieve the goals of Paris Agreement. And there is a number of other things. For example, when there is a trading of the emissions is done between the countries under Article 6, there should be a general mitigation achieved through this trading, so the emissions in general in total should go down anyway. And the Article 13 calls for the enhanced transparency. Can we actually achieve the transparency under what we are doing? And here is a small challenge for you. If we look at the objectives of Paris Agreement, we are talking about the temperature. And the temperature is controlled by the radiation balance, what stays in the atmosphere and what leaves the atmosphere. And a radiation balance is controlled by the concentration of the gases in the atmosphere. So the greenhouse gas effect is controlled by how many molecules you have in the atmosphere, and not exactly how many molecules you put there. But the Paris Agreement talks about achieving 2 degrees by controlling emissions. And emissions are calculated on the basis of activity data, like what activity, economic activity you perform in the country, multiply them by emission factor, like what is the number associated with a particular economic activity, and then you calculate the total. And your commitments are taken on the basis of that number. But here you can see the disconnect. Like, okay, so if it's the amount of the gases which controls the temperature, so how does it connect to the emissions? Well, if we look at the carbon dioxide in the atmosphere, which is main greenhouse gas, so we have anthropogenic activity, which put on emissions in the atmosphere. We have changes in land use, land cover, which puts the emission in the atmosphere. But when something happens, about 25% of those emissions is taken up by the forest, and about 25% is taken up by the ocean. So the concentration is formed by what we put in and what goes out. And this is very important to understand, that you cannot actually control the 2 degrees just by looking at the emission. You need to look at what stays in the atmosphere, basically concentration. And concentration is what we can measure. We can measure concentration directly. We have a whole global network of the measurements stations which perform the high quality measurements of greenhouse gases in the atmosphere. The Global Atmosphere Watch program actually provides this long-term coordination of greenhouse gas observations since 1989. And we have developed the protocols and procedures, how would you perform the measurements? And we also developed the regular process of updating those processes and protocols. And where we stumble is that you can see that observational network is pretty sparse. It's not enough measurements to actually drive decision all around the globe. So that would be really great if we have a further development in the gas sensing that would allow precise measurements of atmospheric composition with a reasonable cost and with a reasonable maintenance of the equipment. So based on this observation, we produce a number, which is the global number, because the measurements are consistent, and we can evaluate the trends in the greenhouse gas concentration of the main gases in the atmosphere. And when you look at what is the precision, how precise should you make the measurements of greenhouse gases in the atmosphere to be able to understand the long-term trends, the point is that we have very tight requirements on what is this uncertainty on the measurement. And for CO2, it's a 0.1 ppm in the northern hemisphere, while this uncertainty is required at the levels of about 400 ppm. So it's very precise measurements. And you can see that similar small uncertainty is required for methane, for CO, for nitrous oxide at the pretty high level. And what is one important thing here is that all measurements should be performed the same way. That should be performed following consistent protocols and be presented or expressed in the same units and on the same scale. This is important because we are talking about very small changes at very high levels. So if one lab measures at the, I don't know, scale X, Y, Z, and the other measures at scale A, B, C, you can't compare those data. So you don't know if what you see as a real gradient in the environment or real trend, or it's just the changes between the lab. So that is on the level of observations, but how do we convert it into something which is relevant for decision making? We know that Paris Agreement talks about emissions. So how are emissions are calculated? The emissions are calculated by the process which is called bottom up. So you take all your economic activities, as I explained, multiply by emission factors, and you get your national total. Well, the point is you get annual number, and you get it with a 2 years delay, and it's national total. So you don't know what is the distribution within the country. But this process is very well regulated. So there is a guidebook which is developed by the Task Force on National Emission Inventory under IPCC, which provides the guidance how all the countries do all the same protocols. It's highly standardized. Unfortunately, when it comes to businesses, the businesses use different approach. They also do the inventory, but they follow different protocol, which is called greenhouse gas protocol, which is not always consistent what nations are reporting as a country. So as the process has been established for a long time, is it good? Is it precise? Wow. So the green line on this plot shows what it should be, the emissions of the CFC 11, which is the gas regulated on the Montreal Protocol, based on the inventory. And if we use atmospheric observations of CFC 11 and put it in inverse model, then we can see that since 2011, the emissions are increasing, but this is a substance which is forbidden for production and consumption. Anyway, the emissions are increasing. So the thorough analysis of observational data of atmospheric composition actually allowed to define the region where those emissions were coming from. And after the publication in Science, this factory actually was identified by their government, and this factory stopped the production and emissions went down. But you see that due to this bump, due to this illegal increase in emissions, we are off the track with ozone recovery in comparison there where we should have been. So atmospheric observations in this respect provide you the unique guidance on what is happening in the atmosphere. This is a reality check. Is it my commitment doesn't work, or is my strategy okay, or am I doing okay? The atmosphere tells you if this is happening or not. And to get from the atmospheric measurements to emission estimates, we use a technique which is called inverse modeling. And the approach itself is called top-down emission estimate. So you start from the atmosphere and then you roll back your measurement signal. For example, this is an example of the measured signal, the concentration. Then you roll your model back, which is called inverse modeling. So you roll back with a numerical weather prediction, your air parcels, and then you get the map. Where does the gas come from? But then you get a net flux, like this is all the gas which is coming from. Then you need to understand who is doing that. And there is a number of the techniques which can be used actually for the attribution. So you can use either the isotopic composition, because the molecules of methane, when they come from different sources, they are not the same in the isotopic composition. You may have heavier molecules, you may have lighter molecules. So if you look at the isotopic composition and you see what we call a light methane, so it's depleted in the isotopes of delta 13, of the 13 molecule, and in deuterium, you can say that this is a biogenic source. And if the source has very high levels of the delta 13 and the deuterium, that is probably anthropogenic source coming, for example, from the biomass burning, coal or oil and gas exploitation. So that's a unique tool which allows us to go from net to do the attribution with that. And of course, you need to measure these isotopes, and those happen at a very, very low levels. Or alternatively, you can use the co-emitter species. For example, if you have cars, they emit also the pollutants, traditional pollutants, for example, NOx. Or if you have the biomass burning, it is also associated with the emissions of CO. And you can use a tracer-tracer correlation, which allows you to do the attribution. Again, you need to put multi-species gas analyzers that can measure both greenhouse gases and traditional pollutants and get those in the same place. So when it comes to the greenhouse gas measurements and measurements to understand what are the fluxes or what are the emissions, there are three different approaches which can be used. And the first one is a flux chamber, which is a pretty good approach when you want to make the understanding of the processes, like what exactly is a biological process which drives this emission. So you can put it on the soil, you can close it, you can pump the air from it, and you can measure directly the emissions or the flux, what is coming out of the soil or of the ecosystem, which is under this box. The problem with this measurement is that it is sensitive only to the area which is under the box. So if you move it 10 meters, it can show you a completely different picture. So the methodology is good for process understanding, but it's not really scalable if you wanted to understand large scale changes. The second approach, which is a little bit more representative, is called eddy covariance, where you make the measurements of very fast variation in the concentration of greenhouse gases, and you make the measurements of the variations in wind speed, and then you do the covariation of those differences, and you get the flux directly. These measurements can be performed continuously, so you get a continuous estimate of the flux or emissions. And if you put this instrument, eddy covariance, on the tower, you can actually measure and have a footprint of several kilometers under the tower. It's very good if you wanted to understand a small piece of the land, but if you wanted to understand what happens with the landscape signal, like what is it in my whole forest or what is it in my whole agricultural field, you need to go with a more advanced technique, and that is making precise measurements of the atmospheric concentration. And on this plot, on this photo, you can see the tall tower, which has several inlets at several levels, which pump the air for the gas analyzer and make precise measurements. And then the measurements at each level will give you a different footprint, and you can go up to the 100-kilometer footprint with such a tall tower and precise atmospheric concentration measurements. So can we use it actually to help understand the emissions? As I said in the beginning, they are outdated. They just give you the national total, and they are not even always correct. Can we use atmospheric observation to actually help to improve the knowledge of emissions? The answer is yes. We can use precise atmospheric measurements of greenhouse gases and co-emitter species to improve the knowledge of the emission. Here is one example. In New Zealand, there is an assessment of the land use, land cover, and the forest uptake using the measurements of CO2, measurements of the radiocarbon, this is a carbon-14 isotope of CO2, plus the measurements of some other species, for example, carbonyl sulfate, to get the attribution to the photosynthetic activity. And based on those observations, based on this network of the station, there are 3 of those stations, we can see that the uptake of CO2 by the forest is substantially larger than inventory suggests. You can see the gray is it's even an advanced inventory. It's not even a traditional inventory. It's the advanced modeling calculation with a biospheric model of what the uptake should be. And the atmospheric observation shows you 5 to 7 times higher uptake, which is a very good news. If you are working with climate, it's better to see much larger uptake than your inventory guess. And actually, one more important conclusion from this is that the uptake happens in the part of the forest, which is actually old indigenous forest and not the new plantations. So that's a very good hint to the policy making, what you would do, what kind of policy would you do if you want to do the reforestation project, what kind of species would you grow, because it shows you where the uptakes happen. But it's a completely different picture if we move with the same set of observations to Amazon. So in Amazon, there's been a set of the measurements which has been done by our colleagues from INPE. And this set of observation consists of the aircraft observations. So the aircraft observations where the flasks are collected. So you do the air sampling and then analyze them in the lab for the concentration of greenhouse gases. So, and then the aircraft goes on this spiral and you can see the profiles, and then that is analyzed. Such an approach is selected because you wanted to see the whole Amazon. So you need to go pretty high to get a pretty big footprint. So what does it show us? Well, the area which is the most deforested, it has 37% of deforestation in the northeastern part of Amazonia, has a flux of 0.1 gram carbon per square meter per day. So it is a source of CO2. The same is for the area which is a southeastern part, which is 28% deforested. It is also a source of CO2 on this picture, while at the areas which are less deforested, which are situated at the western part of Amazonia, the flux is still close to neutral and not statistically significant. And if we take the whole carbon budget of Amazonia, it is a statistically significant source of CO2 in the atmosphere with a flux of 0.29 picogram of carbon per year. This is an important conclusion because people are buying carbon credits in the part of the world which is actually the source of carbon and not a sink. Similar approach can be done for identification of the industrial sources of methane. Here is an example of the measurements which are done in Canada. And here we move to industrial oil and gas facilities. So looking at this square, there is a number of the observing system which are deployed, including tall towers, including ground-based remote sensing, and including the mobile systems. And based on those observations, and looking at the square, there is a lot of tar sands and other facilities. We can see that the reported emissions, which are in blue, are substantially lower than what is seen from the atmospheric observation, which are the red bars. So after the publication in 2017, the paper on the difference between the observed emissions and the reported emissions, there was a revision of emission inventory. And you can see that the later emission inventory, which was produced in 2018 and 2019, is actually a little bit closer to what the observations are showing. So what would be the call for the community? Can we do Amazon, New Zealand, and Canada all around the world? Well, theoretically, we could do this approach all around the world. The problem is that the atmospheric observational network is pretty sparse. So what we need to do to actually be able to use atmospheric data to support the policy all around the globe is to fill in the missing gaps. And so far, we have pretty a lot of investment going to the satellite segment and pretty small investment going to the ground-based segment, which actually adds a lot of value and allows us to do the things which I presented you for New Zealand Canada, in Amazon, and a number of other places. So what we need to do, we need to increase the global coverage, but also we need to have more scalable instruments. Current instrumentation, which is applied at this size, is pretty expensive. And oftentimes, the labs all around the world, they just cannot afford to buy the instrument. Sometimes the cost of one instrument is the budget of the whole meteorological service in the country. So we need to think how we can develop the better instruments which fit for purpose and which are scalable and mass deployable. And also we need a deployment opportunity, like where can we put the sensors? Who would like to run the sensors? And we need partnering with the cell towers. Can we put them on all towers? Can we put them all around the ocean on the ship of opportunities? Or can we put them on the aircrafts so that they actually do not break the safety of the commercial airlines? So with that, I would like to make just one word of the conclusion, which is you cannot manage what you do not measure. And I think we should start measuring more in the atmosphere. Thank you.
Thank you very much for that, Oksana. Some brilliant parting words there. And again, if you do have any questions for Oksana, please do pop them in the Q&A, and we will try our best to get through all of them at the end when we do our Q&A session. Up next, we have Graeme Lawrie, who is the Global Upstream HSSE Manager at OMV Petrom. So there we are, Graeme.
Thank you very much, Anna. Thank you, Oksana. Very, very interesting presentation. I'm going to look at gas detection from a slightly different direction. But I think the key thing for me about gas detection is that it's one of the few things that actually affects both or all sort of health, safety, and environment. And I think Oksana sort of very much explained, how the environment's affected by gas emissions. And as an oil and gas company, it's something that we're acutely aware of. And so I think it is one of these things that really does sort of impact right across the whole business. Probably the thing that most people are sort of familiar with would probably be fire and explosion. And I've sort of really drawn on things like the fire triangle there, because you need these three elements to be able to establish a fire and explosion. You need oxygen through the air usually. You need fuel, which can be the gas, and then you need heat or an ignition source. And the key thing about gases is that they have this upper and lower flammability limits. So it's not just any gas that will ignite. You need to have the correct mixture of gas and oxygen. You've probably even noticed this if you have a gas hob at home. Sometimes the sparking device is trying to ignite the gas and it won't ignite. But if you blow across the hob, what you do is you effectively introduce more air, more oxygen into the mix, and the ignition will actually start. And basically what you're doing is you're bringing the gas from being too rich into a point where its flammability limit is met and it will ignite. This actually was a major factor for myself and for the company that I work with. We had an incident in Kazakhstan quite a few years ago now, but we had a company that was doing some well repairs for us. And part of this process meant that gas was being brought to the surface, of the well area. And it was out in the Kazakhstan steppes. So it was a very flat area. It was always very windy. And I think what happened was that the company that was doing these workovers hadn't appreciated just how much the wind was actually dissipating the gas that was coming to the surface. And so they got into the habit of not using gas detection because they never seemed to have any issues over the last few years. But then on one particular night, there was no wind and it was very still. And unfortunately, what then happened was that gas built up. It wasn't being dissipated, it wasn't being blown away, and eventually it ignited, and there was a sort of massive fire, and so that is probably the most acute fear, when you're working with gas. The other thing that I've got there on this image, where it says danger, confined space. This is another area where gas impacts many industries, where people physically have to get into an enclosed area, confined area. And what you see in the image here is someone actually sort of monitoring the atmosphere inside. The key things that you can have are either insufficient oxygen, so you need at least 19 to 20% oxygen to be able to breathe comfortably. Obviously, ideally, it's about 21, but it doesn't take much. If it drops below 18 or even below, then that actually is enough to basically cause you to pass out. And the trouble then is, if you pass out and you're in this environment, where there's insufficient oxygen, it can actually have sort of fatal consequences. Again, in my past, when I was a government inspector in health and safety, we had an incident where people working in a water treatment facility, one person had gone into a tunnel to do some monitoring, to do some work. Unfortunately, this person passed out. A colleague saw him fall, didn't understand what was happening, and he went in to try and help the person. He then got overcome by the lack of oxygen. He collapsed. And unfortunately, a third person also went in to try and help. They collapsed. And it was only at that stage that someone actually thought, there's an issue. There's obviously an issue here. And they managed to get proper help. And we'll touch on this a little bit in terms of how we manage emergencies as we go on, because it's critical. But even a confined space, I've also sort of investigated a few incidents where we've had people like welders who, using their welding torches, maybe in a section of pipeline. And what they don't realize is that as they're welding, the welding gases actually displace the oxygen, displace the air. And what starts off as being a breathable atmosphere very rapidly becomes, a noxious atmosphere, and there's a lack of oxygen. And even in something as simple as welding sections of pipe, which wouldn't particularly look hazardous, can be very hazardous. The last two pieces really touch on the health aspects of working with gases and vapors. The one there, in the sort of third section, is actually something it's an old trichloroethylene bath for degreasing metal parts. Today, trichloroethylene is not used because of its extremely harmful effects on the environment. But these trichloroethylene baths were very, very common in many manufacturing processes for degreasing and taking all the grease off, metal parts and rubber parts. The issue here was that you could actually sort of open the bath up after maybe 2 to 3 months. The baths would need to be cleaned out. Someone generally, not in this case, but the industrial scale of these meant that people could actually get inside. And what they wanted to do was to scrape all the grease residue off the bottom of the bath. As I say, they would quite often sort of flush it with air. They would pump air into it to try and make sure that the atmosphere was breathable. But the issue was that when people started to disturb the residue at the bottom to scrape it and clean it, the vapor very quickly built up. It was heavier than air, but it was right in the same place as the people's breathing environment was. And unfortunately, it wasn't uncommon for people to get overcome and occasionally, unfortunately, die as a result of the asphyxiation from the gases. The one on the right is a bit more interesting because this is something that we probably all benefit from, but we don't actually maybe get exposed to. And this is the use of what are called 2-pack paints for car spraying and industrial spraying. The gas, the vapor actually contains something called isocyanate. It can be detected. It is a harmful vapor because it actually impacts the lungs. It sensitizes the lungs. The lungs basically fill with fluid, and in effect, if it goes unmonitored and unchecked, the person then can get very sick and actually almost drown in their own body fluids, because the body's trying to protect the lungs, and the lungs fill with this fluid to try and eliminate this isocyanate sensitization agent. So in this industry, it's been a habit for a long time that people will use these air-fed masks, which enables them to, have a positive pressure so that the air is constantly leaking out, and that the isocyanate fumes don't come into the masks. So, as I say, very much as Oksana was saying about the environment, that's a very key element. But then we have this health and safety issue as well. I'll go to the next slide, please, Anna. So, what can we do about it? So we have a range of different options. Thankfully, there are some really excellent gas detectors available now. And what I'm going to touch on is really the fact that we have these personal gas detectors. This is what you see on the left-hand side. The key thing about a personal gas detector, obviously, it has to be detecting the gases that you're going to be exposed to. And in this particular example, it's very small text. I don't know if you can see it, but it basically has H2S, hydrogen sulfide. It has an oxygen reading. It has a carbon monoxide reading. And then even I can't see the one underneath. So it's critical that you have the gas detector set up for the gases that you're going to be exposed to. In oil and gas, hydrogen sulfide, H2S is a key issue for us. But so is things like hydrogen fluoride. We need to be able to detect different types of gases. Key things that the detectors, obviously they have to be fully charged. They're battery operated. So this is really important in terms of ensuring that the device is going to last for as long as your work activity is going to last. The other thing is that they have to be calibrated. And actually, believe it or not, these personal monitors can be calibrated overnight. So typically what happens is people use them during the day. They bring them back to a central control. They put them in a bank of charging areas. And then every morning, there's a little device that they can put it in. It's called a bump test. They literally put it into the bump test and just make sure that it's calibrated and that it's working. So these are the key things. The monitor must be able to detect the gases you're exposed to. It must be fully charged, and it needs to be calibrated, bump tested. Ideally, you wear this up near your breathing area. So that the detector is basically picking up the same gases as you're breathing in. On the right-hand side, the three devices that you see are fixed devices. They're probably part of a process. Some of them are portable, like the Honeywell one could probably be. We have a facility in Tunisia, and we're working right next to a facility that's making agricultural products. And so we don't need the gas detector for our particular site, but we have these detectors set up to detect when their site actually emits noxious fumes. And this gives us an early warning that there's this gases are in the atmosphere, and we can take appropriate action. Others, the ones on the last two on the right hand side there, they're obviously part of a process. There are key things about gas detection as part of a sort of facility. The key thing is, where is the detector going to be situated? Because if you're in an oil and gas facility, for example, and you're offshore and the device is outside, there is this risk that the wind or the breeze will constantly dissipate the gas. So the wind might actually be preventing you from actually detecting a leak. And it's the leak you want to know about. So it's very critical. Inside, it's not so much of an issue because you're less affected by the environment, and so if gas does start to leak, you can pick it up easily. But if you're outside, the positioning of the monitor is really critical. Just think about it for a minute in terms of your home. If you have a smoke detector, you typically put it on the ceiling because heat and smoke rises, so the monitor would probably pick up the smoke first on the ceiling. But if you have a carbon monoxide monitor, it's probably better that it's installed at about head level, where your breathing is, so that you get this early warning when there's a buildup of CO in and around your breathing area. Again, with the fixed monitors, calibration and testing, Sometimes it's a mixture of automation. They can be tested every day remotely. Sometimes there's human intervention where people can go and just check and make sure and run some tests. Fixed gas detection is usually linked to alarms. And obviously, if you're working in a scenario like an offshore facility or a refinery, you don't want one trip of the alarm to shut down the entire refinery. So typically what they have for gas detection in these types of process plant is a voting system. You'll quite often have 3 monitors. If one monitor goes off, it'll sound an alarm. It'll enable the operator to then do some investigation. If all 3 monitors go off, then it might actually operate an emergency shutdown and shut down the entire plant. So there's a voting system. If it's 1v2, 2 are saying there's no leak, 1 saying there's a leak, it might be the monitor, so therefore investigate. But if all 3 trip, then shut down the facility. So that's basically sort of how these gas detectors sort of work as part of the system. If you go to the next slide, please, Anna. So basically, obviously, every single system that is handling and managing gas can leak, unfortunately. It doesn't matter how well they're made or what products are used. Every system is capable of leaking, and that's what we have to be ready for. We have to accept that that can happen. What can we do to try and prevent leaks? Well, we have things like a planned maintenance program, where every single part of the system is checked or investigated on a 6-monthly, yearly, or even bi-yearly scenario, and it's all managed and recorded. We can have routine inspections, kind of a little bit like what you're seeing in these images here. And we can also have testing. People can go out with monitors and test. As a company, we have something in the region of about 30,000 kilometers of pipelines. And we're constantly going out and what we call walking the line, using a gas detection device to walk up along the line to try and detect if there's any trace elements of gases. A little bit like what Oksana was saying, that we can also use satellite imagery and remote sensing to detect if there are clusters. And if we begin to detect some buildup of methane, then we can go and investigate and try to establish if there's a leak, and if there is a leak, where it's coming from. What causes leaks? Typically things like corrosion. It can be internal corrosion or external. With internal corrosion, as a company, we tend to use like chemical corrosion inhibitors, which we can flush through the pipelines to try and prevent corrosion. Externally, you can use things like cathodic protection and sacrificial anodes to try and prevent rust from building up. We also have human error. It can be something as simple as a sampling point that was left open, which leads to a leak. And key areas where leaks are quite common are things in road, rail, marine loading points or unloading, where you've got a connection and, it's being made and unmade, made and broken. And quite often you tend to get leaks in these areas. So I think trying to sort of prevent leaks is really sort of critical, but gas detection is the one way that we can try to sort of understand and appreciate early if there is a problem, and then we can do something about it before it becomes harmful to the environment, as Oksana was saying, or harmful to people, as I was explaining before with the emissions. One of the things with gas detection that we can also use is something called a FLIR camera. I think it's forward-looking infrared imaging. And it's a camera that will look using infrared technology. And believe it or not, you can actually see gas flowing in some scenarios, particularly for us when it's natural gas. And it really helps us in conjunction with the gas detection monitoring, which will alert us to the fact that there is a leak. But then we can use the FLIR camera to try and identify exactly where the leak is coming from, particularly if it's something underground. Almost all of our plant is underground. And so, it's very important to be able, we dig test holes. We try to establish, where the leaks are coming from. So we can use a mixture of gas detection and FLIR to try and establish where the leak's coming from. Obviously, if you've got a leak, you've got to be very, very careful with digging holes and things. You can't have metal on metal. If you create a spark, you can obviously create a fire. So it's very critical in that sense. Next slide, please, Oksana. Sorry, Anna. Yeah. So we talked a little bit about gas detection. When in some sites, let's start on the right-hand side. In our industry, we have a lot of facilities which have very high hydrogen sulfide content within the gas. Hydrogen sulfide is a sort of terrible gas in many respects, not just for the effects it has on the human body, but most people will probably remember hydrogen sulfide from maybe their school experiments in chemistry, where it has a really terrible smell of rotten eggs. The trouble with hydrogen sulfide is that it only is detectable, this smell only exists when it's in a very, very low concentration, so just 2, 3, 4 parts per million. Unfortunately, the trouble with hydrogen sulfide, and because it's so deadly, is that after it gets up, into the sort of tens of parts per million, the smell becomes undetectable. You wouldn't even realize it was there. So in the low area, it's highly noxious. You can smell it. It's terrible. It's instantly recognizable. But once it gets into its harmful area, it's completely undetectable. The same thing, obviously, for things like carbon dioxide and carbon monoxide. They don't smell. There's no warning. Believe it or not, natural gas is also has no smell. You'll all be familiar probably with turning on your hob and your gas hob, and the gas has a smell. So if it doesn't ignite, you can smell the gas. But that's only because we put a smell into the gas, Captain, and that's what makes it smell. Natural gas itself doesn't smell, and so again, it's extremely dangerous because there's no warning. So carbon dioxide, carbon monoxide, there's no warning that they're there. We also use a lot of carbon monoxide because it can be used obviously as a fire suppressant. So if you have an electrical fire, for example, it's very common to use carbon dioxide in your fire extinguisher to extinguish the fire. Basically what it does is it displaces the oxygen out of the environment. And as you saw, remember in the beginning with the fire triangle, no oxygen, no fire. So if you can actually displace the oxygen, which is what a carbon dioxide extinguisher does. But in a lot of laboratories and data centers now, they use carbon dioxide as a protection device. And essentially what they do is they flood the entire area with carbon dioxide. It extinguishes the fire, protects the data, protects the plants. But obviously what you need to be careful if you've got people working in these areas is they cannot enter these areas until such time as the carbon dioxide has dissipated. Big problem with carbon dioxide as well, like many gases, it's heavier than air, so it tends to sink and sit. So it can be sitting in a trench. You might not realize the gas detection might be telling you that there's enough oxygen, but the minute you go into a low area, you might actually suddenly be in an area with low oxygen. So very critical. So this device on the right-hand side is essentially an escape hood. So for things like H2S, for most workers, you wear this device, the red thing on your on the left-hand side there on your belt, and then if the alarm goes off, you can open up the red package, pull out the escape hood. This one's set up with a filter, so it may be protecting against different gases. But in some offices, in some parts, I remember working in Libya, and because we were on the 15th floor, if there was a fire in the building, we were all given escape smoke hoods. Very important. The critical thing is the training. What you want to be able to do, like the guys are doing on the left-hand side here, is put the gear on, try it out in the classroom, fully familiarize yourself with what to do. These are self-contained breathing apparatus, very similar to scuba, self-contained underwater breathing apparatus. Many of the same positives and negatives. Great thing about the self-contained is it's very easy to move around. If you're on a fixed system with a line, obviously someone has to be feeding the line out. It's exactly the same in diving. But, like diving, the big restriction really with the self-contained is that it's limited. You might get an hour or depending on how fast you breathe, if you're stressed, you're going to be breathing faster. With the escape sets on the right-hand side, you've literally got about 10 to 15 minutes. Some of the smoke hoods work on a very basic rebreathing capability. When you're breathing in oxygen, you breathe in 21%, you only metabolize about 4%, which means you expire about 17%. So if you can scrub out the CO2, which is what these devices do with soda lime crystals, you get a little bit more breathing time. You can keep breathing the same oxygen for slightly longer, but it is limited. Typically on a well site, if you go to an H2S location, they have a windsock. The advice is alarm goes off, put your escape hood on, and then move yourself upwind, because the gases obviously will be blown away by the wind. So if you can see the sock and then position yourself such that you can get up above it, upwind. And as I say, typically they have about a 10-minute life, very similar to a smoke hood, really just enough time for you to be able to help. But the key thing, the training, make sure you get familiar with it. We'll just go to the next slide, Anna, please. So just very, very briefly, like a lot of things in gas detection, the key things are, emergency management. We plan, we prepare, we have documentation, we drill. This is what you see on the left-hand side there. We create scenarios where we test ourselves to see what works. Every single drill I've been involved in, it's never gone 100% smoothly. We always have some issue. We learn something. The key thing is when you do learn something is that you apply that learning and make sure that the plan and the preparation becomes better. So, gas detection is extremely important in our business. It saves lives and it protects the environment. So with that, I'll hand back to you, Anna. Thank you very much indeed. And I'll answer any questions that come up later. Thank you.
Thank you so much, Graeme. That was a really important thing to say with the learning. It is all about taking it in and then actually putting it into action. If you do have any questions for Graeme, do pop them in the Q&A at the bottom of the screen there, and we will get to them at the end. So we will be moving on to our last speaker, which is Dr. Matthew Dyson, and he is the Principal Technology Analyst at IDTechEx.
Hi, good morning, everyone. Just about still morning, I think. So yeah, thanks very much for the opportunity to speak today. And so I'm going to be taking perhaps a slightly different slant from the previous two speakers and talk about some of the both technological innovations and application opportunities for gas sensors. So I'm here representing IDTechEx, which is a market research and intelligence firm looking at emerging technologies. So just very briefly, we provide research, reports, consultancy services on a very wide range of technologies. So personally, I cover sort of sensing and printed electronics, that kind of thing. And our aim really is to look at technologies that are developing around the world, from universities, research centers, startups, that kind of thing, and try and sort of identify some trends, patterns, understand those innovations, and then sort of try and establish which of these we think are going to be most useful for which kind of applications. And so over the next sort of 25 minutes, half an hour, I'm going to be giving you a brief introduction to some of these gas sensing technologies. We're going to look at their use for air quality monitoring. And then we're going to talk about a sort of relatively recent innovation, which is these digital nosers that some of you might be unfamiliar with, that are quite a kind of exciting approach to gas sensing that sort of work in a slightly different way to the conventional ones. And then we'll finish, of course, with a sort of outlook and summary. And basically everything I'm going to be talking about today is taken from one of our market research reports on gas sensors. And so if you're interested in finding out any more about that, or interested in anything else that IDTechEx offers, do please get in touch at the email address at the bottom. So on with this general introduction. So I'm sure that, given the audience today, we're all familiar with the basic idea of a gas sensor. We've got some kind of atmospheric molecule, or perhaps particulate, and typically we want to establish what the concentration is as a function of time. And there's different ways in which you can do that. You can have some sort of chemical interaction where there'll be some sort of surface will be functionalized to preferentially respond to particular analytes or chemicals in the gas. and then that will change the voltage or generate current, something like that. Or you can look at them with infrared light, as was mentioned, I think, by the previous speaker, and different molecules will preferentially absorb in different spectral regions. And so by seeing how much of that light gets absorbed and looking at the spectrum, you can determine the absorption and hence the concentration. And then, of course, if particularly for things like sort of particulates and soot, which we could debate whether those count as a gas, but they're very often kind of bundled in there, then optical particle counters looking at reflection from the particles is also another kind of method here. But today we're primarily going to be focusing on these chem resistor type applications where there's some kind of physical or chemical interaction rather than just reflection or absorption. So if we have a look at the concentration of various different compounds that we might find and some of the different sensor types available, you can see there's a really wide range of gas concentrations. CO2 is relatively high concentration. You know, there'll be various kind of toxins, if maybe in an industrial environment, or fairly niche compounds that would be much lower. And establishing the kind of relevant sensitivity range for your technology is obviously kind of absolutely imperative. There's absolutely no point using your sort of infrared sensor to try and detect really low concentrations, because you'll be wasting your time. And so that's sort of one thing to consider. But it's not the only thing to consider. You know, there's the obvious metrics of things like sort of cost and size and power consumption, but there'll be kind of some more subtle ones as well, such as the, you know, how long does it take the sensors to become contaminated? You know, do they require heating? Those kind of things. And so on the next slide, I've got a whole range of different kind of gas sensing technologies, and we've divided those up pretty much into three distinct categories. So up at the top, we've got the established technologies. These were the ones on the previous slide. And so these are ones that you can go out and buy. You know, the gas sensors that we've shown by the previous two speakers, sort of underneath those plastic covers, I'm sure are some of these. So all of these technologies are pretty established. Where some of the sort of innovation is happening is in these emerging and research phase technologies. That's where there's some quite kind of interesting stuff going on that could potentially make sensors smaller and cheaper to make. So as the first speaker emphasized, and kind of reducing the cost of these things is quite important if you want to have you know, just a sort of denser network of sensors. If you want to build up a really clear spatial picture of how gases are dispersing around, then just reducing the cost of these things is really important. And so that's where some of these technologies like printing your gas sensor, maybe using carbon nanotubes, maybe using some other kind of sort of functionalized semiconductor that will you know, chemically bind to the gas, can be really desirable, because in principle these can just be printed sort of directly onto paper, which is of course really cheap. You then probably have to pay for the additional electronics, but even so, it's significantly simpler to make than many of the existing technologies. And there's even applications for these in things like smart packaging, where you could imagine putting some of these in kind of packets of meat or fish or something, and then, you know, receive some electronic warning or label telling you, you know, how updating the use by date or something like that. And then down at the bottom of this slide, there's a few more technologies that are kind of in the research phase. So these are all kind of still at universities. I think perhaps the interesting one here is a quartz crystal microbalance. So if you're not familiar with these are an incredibly sensitive way of detecting very small amounts of material. So if you're looking for a really low concentrations of some dangerous gas and you wanted kind of an early warning, then what will happen here is that a particular molecule will preferentially attach to some vibrating piece of quartz, and that additional mass of that extra molecule, or probably a few of them, but that additional mass will very slightly change the oscillation frequency, and that can be detected. So there are technologies coming along that could enable kind of much higher sensitivities than some of these more traditional sensors at the top, and of course that can open up a few new applications. So if we take a look at a specific example here, I think one of the trends that we can see is a reduction in size, and I think that's pretty much true kind of across the sensing space. Whichever type of sensor you look at, there's generally speaking an endeavor to make them smaller and more compact. And that's why we have smartphones today that are so capable, that have got all these cameras and accelerometers and all kinds of things in there, because these sensors have got really small, got smaller and smaller over time. So we take a look at this little graph here. We can see that these are getting smaller, and also as you reduce the size, you typically reduce the power consumption as well. And so you're now with these tiny little MEMS sensors, which stands for micro electromechanical systems. And so these things are kind of a few millimeters across. Perhaps the best known application of MEMS is the accelerometers in smartphones or smartwatches, but you can make gas sensors this way as well. And then over on the right, I've got another innovation, which is even smaller than that, where a little bit of metal oxide has been printed here, that will then slightly change its resistance as gas molecules are absorbed onto the surface. And you can see how small this is. So here's I think it's a German organization. So here's a €5 cents, pretty small coin, and you can see that these little sensors are extremely small. And so there'll be a little bit of little platinum heater in there, and then there's a little bit of metal oxide that will then detect your gas. So I guess the point here is that there's a really, there's a huge array of sensing options, with lots of endeavor to make them more sensitive, more selective, and smaller. And we've kind of summarized that on this chart here, in that what do people want? They want to be able to detect lower concentrations. People of course want specificity, particularly especially for industrial purposes, maybe for unusual gases, and of course the kind of smaller size as well, with the benefits of making them enabling wider networks, getting better spatial distribution, but also incorporating them in new places. Can we get these gas sensors in smartphones and smartwatches, and maybe other types of wearable technologies, e-textiles, and that kind of thing. So I guess having discussed this range of sensor types, I think that the next place to look at is some of these applications of gas sensors, and there's more than you might perhaps imagine. And so we've heard today a lot about sort of personal safety in an industrial context, and also looking at sort of unwanted gas leaks from mining and refining and sort of the resource sector. But there's quite a few others. Things like catalytic converters, maybe not necessarily quite so obvious, with electric vehicles. That's probably a declining market. But as we move from left to right here, there's sort of growing opportunities that you might not necessarily be thinking about. So one of these is the sort of smart cities, and certainly if you live in London, you'll know that the mayor is very concerned about air quality, and of course he needs data to back up his new regulations. And so having all of these sensors distributed around the city can certainly assist him with that. And you can imagine a world in a few years where this will be kind of more dynamic, where let's say road pricing responded to gas pollution levels. So rather than just a kind of arbitrary charge that still penalizes you even if it's late at night, you could sort of preferentially direct traffic to less polluted regions, or discourage people from venturing out into polluted regions at particular times of the day, maybe when there wasn't much wind or something like that. And so that's how gas sensors fit into this idea of a smart city, where you can have kind of real-time monitoring of these metrics, and then use that information to adjust demand via pricing, and that could have a really significant impact without penalizing people who maybe needed to get into the city for some particular purpose or an unusual time or something. There's also opportunities in smart homes for indoor air quality. And this is a sector that we've seen kind of increasing amounts of interest in, particularly post-COVID. People around the world are more and more concerned about the quality of the air that they're breathing, both at home and in the office. And so having gas sensors that can keep them informed of that, maybe make adjustments to the heating and ventilation system, or advise them to wear a mask or something like that, is quite desirable. And then companies in the automotive sector, the same logic applies really. People want to monitor the quality of the air inside the cabin, know when to turn filtering on and off, and that kind of thing, when to recirculate the air automatically, that kind of thing. And then we move up more towards these kind of emerging sectors. And again, there's some here that are maybe a little bit less obvious. So it will start at the bottom this time. So battery monitoring is obviously really important as we go towards the EVs. And we want to make sure that there's no risk of fire. And as any of you who've seen the back of your phone kind of expands disconcertingly will know that when the lithium-ion cells sort of begin to fail, and they very often produce gas, if that starts to leak, that's very much something that you'd want to detect as early as possible. And then over on the far right, something that's perhaps slightly less serious, but nonetheless important to the car companies that a couple of startups are looking at, which is trying to quantify the smell of a car. So, you know, allegedly, if you sit in a Mercedes, it smells different sitting in a BMW. Well, why is that, and can they quantify it? And at the moment, they just hire kind of experts who are very sensitive noses who can try and discern these different smells. But if you could quantify that by looking at a whole matrix of volatile organic compounds, that'd be a really desirable application. Working my way upwards, you've got cancer diagnostics. Apparently, you can get some kind of medical insight from looking at the volatile organic compounds in people's breath, and obviously, the more sensitive you are, potentially the earlier warning you could get. You could obviously incorporate that into wearable technologies to monitor people's breathing, or during exercise, or if they were ill, you could again monitor the air that they're exhaling and see if you can detect any variation in the gas. And then the one I mentioned earlier, which is the smart packaging for not having arbitrary use-by dates, but instead just kind of adjusting the use-by dates and tracking items throughout the supply chain. Obviously, for kind of organic things, you can see if they're close to spoiling by looking at the gas that's being produced. So there really is both a very broad range of sensors and a very broad range of applications. And I think so. I think it's a relatively sort of exciting time for the gas sensor market, people supplying these sensors, and also the people supplying the software and the sort of associated business models that go with it, because you can really use this data from the gas sensors with all kinds of digital tools to get some really useful insight, as with my example of these smart cities, that would be very, very difficult to get otherwise. So I guess having outlined all of these opportunities, I guess the question is who's going to benefit from them? And broadly speaking, we see quite a big opportunity for industrial players to kind of transition to the kind of environmental space. It can be tricky to kind of go the other way, because you end up with these industrial things being safety critical, and that requires sort of additional regulatory requirements. People are reluctant to try out a new technology if it's safety critical, that you can sometimes have harsh environments that are quite hard to design for. You get those kind of challenges. But I think there is an opportunity for companies that have got a long history of supplying gas sensors for the industrial market to say, oh, actually, sort of city councils want to distribute sensors around their cities, or people want them in their offices, or they want kind of dynamic heating and ventilating systems rather than ones that are just kind of controlled with a thermostat. We want to be dynamically monitoring air quality. It's not necessarily safety critical, it's still a building, but there's a big opportunity there. And so that's the kind of, broadly speaking, the direction that we see. It's the direction that we see companies being able to take advantage of some of these new applications. So looking a little bit more specifically now at the air quality monitoring. So I've got a kind of couple of examples here of just a sort of typical house and where you might want the kind of type of chemicals you might want to be monitoring in particular locations. And the obvious ones here are things like particulates and nitrogen dioxide, and of course carbon monoxide in the kitchens. And people have all got these carbon monoxide sensors and smoke alarms, and this is all pretty established, but it's can we make that more sophisticated? Certainly I don't have anything for kind of sensing any mold or anything mold in the bathroom when it might first appear. I'm not monitoring for other kind of volatile organic compounds that could give me indication that maybe there's a leak somewhere, and say some floorboards are rotting or something like that. So there's opportunities to use these sensors not just for health, but also for predictive maintenance of your property. And of course, as I'm sure many people are aware, all of these different gases, or many different gases, can have kind of negative health consequences. So there can be a real driver for people to want to adopt this. As we see, encouragement for everyone to get carbon monoxide alarms, I think is one that's kind of been solved, but maybe some of the other ones perhaps less so. Sorry, wrong way. And so if we have a look at how these might be used, I think how these sensors might be used, I think that the big opportunity here is in integrating them with heating and ventilating systems. And perhaps in the UK, at least in domestic houses, that's a little bit less relevant. If air conditioning is still a bit of a luxury. But of course, in many countries, air conditioning is completely standard. And so you could absolutely imagine organizing your heating and ventilating with a network of gas sensors distributed around the house, and in the same way you might in an office or hospital or school or kind of larger building. It already exists to some extent, that kind of infrastructure, but there's opportunities to do it to a greater extent. And I think that one of the key points here is over on the bottom right, which is that many consumers don't put a lot of value on the air quality sort of in their house. It's not something that consumers are typically worried about. And if you, despite the fact that could have long-term impacts on their health. And so if companies are able to sort of market effectively and suggest to consumers and even people running offices or schools that monitoring air quality and hence using that information to make adjustments to the ventilation system could improve the performance of their workers or keep their children healthier and happier or whatever it is, then there's a real opportunity there, which is a bit of an untapped market currently. That said, there has sort of been more interest in it with COVID, which has, of course, led to kind of people caring more about sort of ventilation and leaving windows open. And we were all sort of encouraged to open windows. We had friends around at least a few years ago, and so we see a kind of interest in Google searches over time. There's the usual kind of seasonal peaks, probably around hay fever. We see a kind of spike during COVID. With people getting increasingly interested in how they can purify their air, which of course links to gas sensing. And we've also spoken to a few gas sensor companies. I'm not going to list them here, but those companies saw considerable growth in sales during the pandemic. More than doubling. So that there was a real acceleration of interest in sort of indoor air quality over that period. So I think, when you kind of consider how these air quality monitoring could be utilized, there's kind of different levels of sophistication here that could be chosen. So sort of on the most basic level, I can just get a sensor in my house that turns a red light on when I need to open the windows, which would be kind of extremely cheap and extremely simple. In contrast, you have something much more sophisticated. You could imagine a widely distributed network of sensors throughout a building or even throughout a city, all dynamically feeding back into some sort of building control software, and then maybe potentially even doing road pricing. So there's huge range of opportunities from the really straightforward to the much more sophisticated. And there's a few people kind of trying to do this kind of thing already. So here's a few examples of some that are commercially available, aiming to target these kind of smart home markets. So it's not kind of completely new, but I think this is a trend that we'll see being sort of adopted more widely as people are kind of increasingly concerned about their environment and their health, and governments place more of an emphasis on air quality. And so this, obviously the addressable market of kind of all households is huge. And so I think that's a real opportunity for companies in the gas sensing space. So the next topic I'd like to talk about is perhaps a little bit more technical, and it's this idea of digital noses. And so what does that mean? What it means is that you're trying to detect a kind of smell or odor in total rather than individual constituent. So most gas sensors that people talk about are trying to detect carbon dioxide, or carbon monoxide, or whatever, sulfur dioxide, whatever it may be. Here, what we're trying to do is detect the concentration of each of these, and also to kind of just parameterize the smell as a whole. Because if you think about all of the different kind of sort of senses, as it stands at the moment, I can easily send someone a digital file of sound or video is extremely standard. But if I want to tell my friend how something smells, well, what do I do? And realistically, I have to try and describe it, and you end up, the kind of words you get on the back of a wine bottle. It's extremely difficult to quantify. And so what idea of these electronic noses is, the kind of big picture here is that you can quantify smell in the same way, so digitally, in a similar way that you might with pictures or sound, And hence you can say, oh, I know that these wines smell exactly the same, or when we make adjustments to this wine or perfume or whatever it is, this is what I'm looking for. And I'm not just relying on an expert or just on a comparison, I'm relying on something much more quantitative. And that's really tricky because smell is really complex and it involves a huge array of different volatile organic compounds. And so the typical way in which this is done is that you have a multiple sensor array. So there will be some kind of array of sensors. Each point on the array, each pixel, if you like, will be functionalized slightly differently, and they'll all respond slightly differently to the gases in the air. And hence, each kind of smell will have a different kind of overall response. There'll be slightly different relative detection rates between these different pixels. You can obviously apply some software here, some supervised learning, that kind of thing, and determine both individual gas concentrations, at least for the major components, but also kind of parameterize that smell. And so this is that concept is kind of illustrated here, where you have these different sensors tuned to different molecules. You have two different smells, and they will give you, different concentrations of each. And then you can say, oh, well, each of these gas mixtures contains different proportions of these components, and so we can kind of group these together and hence identify the different smells. And there's various ways to make these sensors. You can do sort of printed arrays of sort of semi-functionalized semiconductors. And there's also optical approaches where the speed of light traveling through different materials that interact with the gas will change slightly. So this all sounds very encouraging, but where are we along the sort of development curve? And so here we've got the kind of classic hype curve that if you've looked at new technologies, you might well be familiar with. And we're sort of putting it kind of somewhere here. There was quite a bit of hype about it a few years ago. And now we're just sort of seeing these gradually, people are in discussions with the automotive manufacturers and the wine producers, the perfume producers, people for whom quantifying smell has real value. And so that's kind of where we see this technology. And you can make these things kind of relatively simply, as I say. So here's an example from a research center showing these printed arrays of CNT carbon nanotube sensors. And then you have this kind of this fingerprinting where each selection of gases produces kind of a different overall response. The individual pixels will respond slightly differently. People are already doing this, things that you can go out and buy now. So just a couple of examples of these digital smell, digital nose type opportunities. Again, using different technologies, but also integrating into software as well. I saw some nice examples from Bosch where they'd be able to put one over different types of beer and tell me all about them just from one of these little sensors, which was rather nice. So that brings me kind of to the outlook. So broadly speaking, towards the end of the talk, and so I think we just sort of try and wrap everything up with a sort of typical technology roadmap. Which is the kind of thing that IDTechEx does for a very wide range of emerging technologies. And so here we've got, and I'm not going to go through all of these, but here you can see that we've got sort of historical things down the bottom, going up towards emerging at the top, divided across these kind of four categories. And you can see there's a lot of innovation in this space. And I think as time progresses, we'll see new materials being used for new applications. We'll see more and more use of kind of quantifying smell, which is something that hasn't really taken off. There aren't standardized file formats that people are sending around to each other to describe different smells. It's all very verbal. There's nothing kind of sort of tangible or scientific about it. So I think those are the kind of trends that we'd expect to see. And some of these markets, as I say, are really quite large. The sort of smart home market, the smart packaging are both pretty significant opportunities. A couple of sort of specific examples that I haven't really touched on thus far are using gas sensing for in the medical space. Again, using the fact that people's breath can actually give you quite a lot of indication about their well-being, and you can imagine these sensors being either used kind of at home or in a hospital. And again, as the sensors get smaller and cheaper, more and more opportunities for people to do this at home or in their local surgery. I don't have to go into a hospital, and it's a whole nother metric that fits in with sort of narratives around digital health. So it's not just about measuring blood pressure or temperature or heart rate. If you can measure the volatile organic compounds that you're exhaling, you can add that to build a more complete picture of somebody's health. And there's also opportunities in the automotive sector. that's undergoing quite a big transition as we move towards electric vehicles, and that the gas sensors that would have been needed around an engine, obviously aren't required anymore, but there's still a need for battery monitoring, and there'll be more of an opportunity for things like cabin air quality, because it's probably a bit more perceptible without the kind of slight aroma of a car engine that typically smells sort of a little bit of clutch and oil. That will disappear, and so there's definitely scope there. And also for things like monitoring driver alcohol consumption is something that you can definitely see being widely adopted. So that brings me to my final slide. And so just to kind of sum up with the sort of 3 main points, first of which is that gas sensors aren't really a technology in isolation. I think that the opportunity for them is when you kind of combine them with software, and you use them as an input to some kind of big set of data where you can operate on it and then achieve something else, like redirecting traffic or something like that. So there's a real opportunity to not just see them as I'm selling a gas sensor, but I'm selling a whole solution which happens to use data from gas sensors. The e-NASE is a really exciting innovation, and the idea that you could perfectly describe a wine to someone by sending them a digital file is relatively compelling. But it's, again, a lot of the effort here will be around the software, and also what do I do with that information? Can I reproduce these smells? Is another interesting question. And then the trends in manufacturing. So this trends towards printability, towards miniaturization, scalability, and I think those are probably true across most types of sensors. So that brings me to the end of my talk. I think I'm just about on time. So hopefully you found that interesting, and thanks very much for your attention.
Thank you very much, Matthew. Did you say that was you done now? Yeah.
Yeah, that's it. Yeah.
Perfect. No problem at all. Well, thank you very much. That was a fantastic presentation and great market insights. And now we'll move on to our question and answer portion of the webinar, where we will be giving your questions to our speakers to answer live. I can see that a few of them have already been put into the Q&A and answered via text as well. So what we can do is we can just read those out as well, just to make sure that everyone can get the opportunity to hear the answers, and to give the speakers a chance to maybe elaborate a little bit more. And so we can start with the one we received for Oksana about can your research be used by small and medium companies who are looking to reduce their carbon footprint?
Yeah, I already answered in the chat, but I can just reiterate that indeed you can use atmospheric observation actually to get the understanding of the emissions of the particular facility. So we've been looking at the number of cases where, for example, there were evaluation of the emissions from the wastewater treatment facilities, for example, or the big dairy farms, where you can use atmospheric observation to get the footprint or the emissions coming with a specific facility, which is usually downwind of what you measure. What we cannot do is we cannot evaluate the emissions for the full value chain, right? We can talk about the direct emissions from the facility, but if you wanted to understand the whole value chain, when you understand the carbon footprint, for example, the emissions which are related to the transportation, consumption, reutilization, that will be pretty difficult. So you would stick to the inventory. But if you wanted to understand the carbon footprint of the particular activities, you can make the measurements at the facility. Or if you do for example, the negative emissions, then you use the technology to pump CO2 from the atmosphere, you can make the measurements to see in the atmosphere if it actually get out of the atmosphere or not locally. So you can set up the measurement system to understand it locally.
Fantastic. Well, thank you very much. I hope that answers this person's question. We have another one for Graeme, or a couple here, that you've already answered. I just wondered if you might also want to reiterate. And the first one is, what advice do you have for procuring gas detectors?
Yeah, no, that's a very good question, Anna. I think the key things that you know, as an international company, we tend to like to approach companies that have a global reach, so that we can deal with them in, you know, the Far East, the Africa, the Middle East, maybe even the United States. I think though, in terms of, you know, what we often want for the companies that we work for, it's a long-term contract. We want to establish, you know, a good relationship with them. The after-sales care is very important to us. If the company is prepared to give training and send people to our facilities to help, not just the people using the devices, but maybe even the people that are going to be maintaining them and managing them, and, you know, having a good relationship with them, such that, you know, if we have a problem, we can call them up 24/7, you know, and get help. So, you know, I think we very much approach it from the point of view of basically a relationship with them. And as I say, you know, quite often, like a lot of things in HSE, it's not down to the lowest cost. Very often it's actually about you know, getting a good service. And if that's twice as expensive as someone else, that's where we'll go. Yeah.
Perfect, fantastic. We also have another question here about how you can incentivize employees to wear and maintain their wearables and comply with these safety policies.
Yeah, no, that was very interesting, because that's the one thing I think that doesn't matter what industry you work in, it's a huge challenge. I think that the one thing that we've realized is that if you can give people a choice, if you can give wearers an opportunity to say, oh, this device, I like this device because it's simple to use, it's lightweight, I understand how to reset it, or, you know, so, you know, I think giving people an opportunity to choose what they want to use is good. I think we do, like a lot of companies, have recognition schemes. And I was saying in the chat that you just need to be careful not to be patronizing. You can't just come up to someone and say, oh, you're wearing a dust mask, congratulations, great, you know, here's recognition, because that may be perceived as patronizing. But, you know, when we have people maybe that are working in confined spaces and there's a lot of benzene exposure, which we do have, quite often the people have to come in and out every time the alarm goes off. You know, so it can be very sort of stressful. But typically, as I say, with these people, we do recognize them, we do reward them with good behavior. And I was saying in the chat that it's not uncommon for us to give someone a gift of an iPad because they've done a really good job, because it sets a good example, and other people look at it and say, wow, you know, the company really means this. You know, it's not like a t-shirt or a hat or something that they might not wear or might not like. This is something that they can bring home to their family and, you know, make good use of. So I think recognition is a huge help when it comes to encouraging people to use and wear the right monitors and devices. Yeah.
Perfect. Yes, that definitely sounds like a sensible idea. And I can agree that maybe it would be a little bit patronizing to reward every little tiny thing, but that definitely sounds like a good workaround. Thank you for answering that one. We have one in the Q&A also for Matthew. What would you say is the most promising innovation in the market at the moment?
So I definitely say these e-nosers are the most promising. I think it would take quite a long time for them to become kind of embedded in sort of everyday activity. But this idea that you can sort of quantify smell, I think ultimately is quite powerful. You know, we've you know, it's taken quite a long. If you look at, say, quantifying images or quantifying sound, so that we can sort of send sound files around or send videos around, that's kind of completely transformed how people communicate. You know, could you sit there and probably not to quite the same extent, but you could imagine, you know, car companies ensuring that all their cars smell the same, even in different jurisdictions, or this kind of thing. So the idea that you can kind of put a digital sort of template, a sort of digital marker on a particular smell, I think it is ultimately quite an interesting idea with loads of different applications.
Well, definitely, I agree. It's a fun concept, but as well, almost incredible to think about it, as it's one of our 5 senses. You know, it's a hard thing to put digitally. So just the thought of it is pretty incredible. So thank you very much for answering that question. We have another question for Oksana. What are your expectations for COP28?
That's a very difficult question because the expectation is that this is the first global stocktake, right, where all the governments actually looked at what are their achievements. And if we look at what is going on currently in the context of the global dynamics, climate dynamics, I mean, that we have El Niño and we are kind of touching 1.5. I think that there will be pretty active debates on, like, are we really on track, or are we just cheating ourselves with all the massive achievements? And the political process is very complicated, because I've seen the document which is related to the first global stocktake, and there's a lot of complexities which are wide in the document, which are related to the equities, equalities, equal responsibilities, differentiated responsibility distribution. So basically, if you look at the whole socioeconomic concept, which is attached to the climate mitigation, out of this huge document, there was only one paragraph which was saying, like, hey guys, the concentration are increasing and we're getting to the very close to a temperature target. So it's in a way biased towards the human society rather than to the physical problem which is behind. And if we don't start really at a physical problem and start connecting the physical problem to the socioeconomic reality, we are lost. Because while we will be deciding who is responsible, we may actually lose all the possible targets. So I hope that there is a recognition that we need to run fast, and we need to run all together and stop kind of making I understand it's a complex issue, but let's try to do something rather than take the commitments and just blame each other that you are not doing that.
Yes, I definitely agree. It's unfortunate that it boils down to a political issue, especially with, as you were saying in your presentation, the measurements and the data is there to say otherwise and things, and it's hard to argue with something so concrete as data in front of you. So thank you very much for answering that question. We've got another one here for Graeme before I move on to our more open questions, that says, what, if anything, can be done to help limit worker exposure to gas?
Yeah, no, I mean, that really is the critical thing. And I think a lot of, what Matthew and Oksana were saying really is that technology is a huge help in this respect. A lot of our oil and gas facilities now are not normally manned, not peopled. And so gas detection, for example, is then highly critical. You rely so much on the technology to tell you if there's a process problem, because if something's beginning to leak, obviously you want to preserve the system, you want to be able to preserve the facility. And typically what we would do then is, either fly people offshore to go and take care of essential maintenance, or, bring people in under a controlled environment. But the people aren't exposed all the time. A lot of the old, the typical sort of Piper Alpha type situation, where a lot of people are exposed. We're trying to sort of move away from that, having even things like drones and robots and things that can actually sort of take sensors into areas now and deep into areas and actually do gas detection remotely, such that the operators are sitting in a nice, safe, controlled environment, but the technology then is enabling us to make sure that the area is safe and take care of maybe identification of potential leaks, that type of thing. So I would say a lot of particularly what Matthew was explaining in terms of the technology that's available today in many different industries is really helping to reduce worker exposure and take the people away from the risk. So yeah, it's great.
Yeah, that's a really interesting point, actually. I think especially with a lot of industries, people are almost afraid of all of these new technologies that, automation is taking over jobs and things, but this is maybe one situation where it's actually the ideal situation. It's protecting people and things, so that's quite good to look at. So thank you for answering that question there, Graeme. I've got, I think, two more here, and I think we'll we'll make those the last two that aren't directed at anyone in particular. So please feel free to jump in, any of our speakers who would like to answer first. So the first one is, what's the most important aspect of gas detection?
I think possibly more of a technological question, so I'll answer that one. I think obviously it depends a lot on the application, but I think, you know, as with any kind of same as any kind of sensing, really, reliability is kind of key, particularly in these safety conscious issues, as Graeme was saying. You know, you don't want false positives, and you obviously don't want false negatives either. So that would be one of them. And then, of course, is, you know, for some applications, obviously the sensitivity is important if you're trying to develop a new technology. For, you know, you want to get the kind of earlier warning, and clearly that's important. But I'd say that just knowing that your gas sensor will work when required, particularly in a safety context, is the most important.
Definitely, I think you've hit the nail on the head. That one, making sure it works is probably the thing that you want from your gas detector. Would anyone else like to add into that at all?
I just reiterate basically what Matt said. You know, I think reliability is probably the critical thing. You know, you rely on it so much. In our capacity, it saves lives, so it has to work. You know, and that sort of easy to maintain, easy to wear, easy to use, and reliable key things, really. Yeah.
Absolutely, I think that reliability as well, because at the end of the day, you want an accurate and a reliable result, don't you? And something that you can actually use. So I think we've pretty much answered that one. The last one, is funnily enough, how can we assure more reliable and accurate measurements?
Well, probably I can comment a little bit here how we do it through the global program, because actually when we look at the environmental monitoring, we need to make sure that the measurements which are performed by all different countries are consistent. So because it's related to international policy making. So if I measure something which is expressed in the units of apples and you measure something with the units of oranges, it's very difficult actually to develop the common legislation. Like if the convention says that this is a level of the I don't know, a particular pollutant which is acceptable and tolerable, and all the exceedances should be actually punished. I mean, how would you actually compare with your exceedance if you don't even measure on the common scale, or if you don't express any common units? So I think how to make these measurements reliable and accurate is that it is super important, in particular for the emerging technologies, to have common protocols and a common measurement standards. If everybody measure following different standards and protocols, you cannot compare the data, and you cannot actually get the exposure correctly, because then you don't know what it is exactly you're measuring. And in the global programs, if we need to compare, particularly between the countries where you have this policy moment, like, do we agree actually that this is what it is? So we need to have international standards, and we have the internationally agreed primary standards, which are used for the traceability. So you actually calibrate your instruments following the same gas standard all around the world, so you know the traceability. And also, well, I know accuracy is a pretty critical issue, so that's related. That's why we use not the gas sensors, but actually pretty big gas analyzers, which are thermally stabilized, and that they are pressure controlled, humidity controlled, and stuff like that. So you can actually, under control environment, you can make very precise measurements of the things we need to measure.
Fantastic, thank you, Oksana. Yes, I suppose we're in that very advanced scientific stage now of we've learned from past mistakes. We can put in control measures and do tests and ensure that these are accurate and reliable. Thank you. Would anyone else like to take on the question, or shall we? I think we've just had one more come in, and I think I'll call that the last one. Any other speaker for this one? No? That's all right, we can move on. So we have one last question then. How can we detect H2 gases using IR-LEL sensor using cross-reference of CO sensor?
I was hoping Matt might take that.
That's a very, very specific question. I don't have a kind of solid answer. I'd suggest that going for the IR spectroscopy is possibly the way to go here. So, most gases, certainly hydrogen, carbon dioxide, and carbon monoxide, will all absorb at particular IR frequencies. The molecules resonate, and hence, if you can then look at the relative intensities by looking at the absorption and then referencing those back to how the sensors perform in a kind of with a known concentration of each gas is probably the way to go there. The difficulty with those kind of measurements is that other sort of gases, moisture, so on, of course, also have a spectrum that absorbs, and so it doesn't enable you to get down to these really small detect really small concentrations, because ultimately we're just looking at a whole block of air and seeing a whole block of gas and seeing what wavelengths made it through and which ones didn't. But I'd say IR spectroscopy was the way to go, to summarize.
Fantastic. Well, I hope that's answered that person's question. Thank you very much again, everyone, for joining us and for your questions, and a big thank you to our speakers for your time and the fantastic expertise that you have shared with us today. If you feel that you had a question that we potentially haven't been able to answer, then do please pop it in the chat or Q&A, or do get in touch afterwards. We will be following up with a communication in a few days, not only with the recording of this so that you're able to watch it back, but also with your questions answered as well. And just another big thank you to our sponsors again for enabling this webinar today. I hope you've all been able to take something away and potentially to take away and pop into your own HSE strategies. So thank you very much. We hope to see you in the next one, I suppose. Thank you, and we hope you have a great rest of your day.